Reject, even though I can. All right, good morning everybody and welcome to the next talk from PyCon AU 2018. Our next talk is from Philip James from Patreon and he will be discussing timing side-channel attacks, which are all kinds of fun. Please make him feel welcome.
Hi there, I'm Philip James. I am Phildini basically everywhere on the internet. This particular, okay. I could describe, there we go, okay. I would prefer not to have to describe the slides. So like I said, I'm Philip James. I'm Phildini basically everywhere on the internet. That is my Mastodon handle where you can find me when I'm not tweeting at conferences. This talk is all in the timing. If you're walking in a little late or have to leave a little early, that's okay. It's all in the timing. And it's called all in the timing because I'm going to be talking about timing attacks, which are a category of side-channel attacks. Before we begin, I'd like to mention that I work for Patreon in San Francisco, and they are generous enough to employ me and keep sending me to conferences. Patreon is trying to build a real funding model for people making things on the internet, including open source software developers. And I'd love for you to come talk to me, to ask me questions about that later, about the work that we're doing. So I want this talk to do three things. First, I want to explain timing attacks in general so that you can see them when you're reading code. Second, I want to show you a real-world example of a timing attack based in Python and what it took to fix it. Finally, I'll show you some more examples of side-channel attacks, and we're going to end with a now infamous attack against Intel CPUs that you've probably all heard of. Speaking of accidentally introducing a timing attack into code you've written, here's a login form I wrote up for this talk. With this web form, someone can submit a username and password, and the system behind the form will give you a yes or no answer about whether the combo was correct. If you think about the login form as letting you try passwords one at a time, we can figure out the right password through guessing every possible password. I'll show the math for how many possible passwords there are. Let's say our maximum password length is 8 characters long, and let's say for each possible character in the password, there are 36 possible characters, the letters A through Z plus 0 through 9. These are close to the worst password rules you could come up with, but they make a good example. The total number of possible combinations here is 36 to the 8th power, which is a lot of combinations. If we could try each password one by one, and it took 1 millisecond to run each guess through the login form, then it would take almost 100 years to try every possible password, and I would probably not live to see successfully getting into your email account. This is actually great. It means that at least in this hyper-contrived example, guessing passwords takes a long time, which means it's harder to break into accounts on the system. But sadly, the way I implemented checking for this form makes password guessing easier than I want it to be. It takes different amounts of time to check the password based on how right your guess is. This will happen because I use the Python double equals operator in the backend to compare the password. This actually isn't Python's fault, it's mine, but to understand why, we need to understand the double equals comparator. If you're using Python double equals to compare two strings, it finishes faster based on how similar the strings are when compared left to right. You can see that here. In the first guess, it ends immediately because the first letter doesn't match. For the next guess, it has to go through 4 characters before it hits a bad match, taking a little longer. And then for the actual correct guess, it has to go through each character, checking one at a time to show that you've actually provided the correct password. Python's double equals comparator is smart enough to stop early at the first character mismatch. Because of this, we can guess the whole string in just 144 tries. Here's how. We saw that double equals get slower and slower the more characters you get right. Instead of having to guess each possible password, we can focus on guessing the first letter. The first letter on average will take 18 tries, 36 divided by 2. The system then tells us through the timing of the return if the first letter is right. We can then check the next one and the next one and the next one all the way up to the full password. That's 144 tries. If it takes us 1 millisecond per try, now that's only 144 milliseconds, and I can get into your email before the end of this talk. That's a lot faster than 90 years. In this graph, the top line is exponential and the bottom line is linear, and this graph is going to come up a couple times in this talk. We want password checking to take exponential time, but because of how we implemented it, it takes linear time. Timing attacks are not interesting necessarily because of how they work, but because they let you do something that should take exponential time and do it in linear time. Let's see the timing in action. Here, I'm using the IPython profiling function called timeIt to show that plain string comparisons in Python have different times for different strings. These timings are still pretty fast, I know, but we're getting measurable differences in how long a function takes to run based on how many letters we got right in guessing, which is kind of crazy when you think about it. We call this data-dependent time because the input data changes how long something takes to run. The advice people give you when you ask about timing attacks is, make everything take the same amount of time. This is called a constant time operation. It's called constant time because it doesn't change how long it takes based on input that your attacker controls. Here's a similar timeIt profile for string comparisons using Django's constant time compare function. It really is constant time, plus and minus some small system noise, but that small system noise isn't really enough to reveal information. Computer scientists like to call this big O of 1 in terms of how long it takes, so you can do that too. To drive this home, I want to talk about a real Python code base that had to fix a timing attack. The attack is a little different than the password example, but the principles and the result are very similar. The big picture is that, thanks to a timing flaw, you could get a signature verification library to generate a valid signature for you. Pretty fun, eh? Let's talk about that one. So we're going to talk about Keysar, and specifically the HMAC primitives that Google published within Keysar. The details of HMAC aren't important for this talk. It's enough to know that HMAC is an algorithm used for verifying data integrity, among other things. You use HMAC to generate a signature from a message, and use that signature later to verify that the message wasn't tampered with. Keysar's HMAC function looked something like this. The way this works is that the message is the raw unverified data, and maybe sig is the signature that someone provided. If you tamper with the message, you don't know how to generate the correct maybe sig, so you'll return false. Can anyone see the timing attack here? If not, if you can, great. If not, no worries. Here's what's going on. I've bolded the last line of the function because it's doing a regular string compare. We saw in the password example that string comparison can be vulnerable to timing attacks. The comparison will stop at the first wrong character of maybe sig. Nate Lawson noticed this attack in 2009 and verified that he could perceive timing differences against a local server. The lesson here is that even though HMAC, the algorithm, is cryptographically secure, the math is all correct, its implementation ended up not being secure because of how the comparison was written. The fix, by the way, was to use a constant time compare function. They chose this one, which works just fine. If you want to understand how it works, we can talk about it after the talk. Anyway, this got fixed in Keysar in 2009. But notably, if Google got this wrong, then all of us here probably could get it wrong too. This is what makes timing attacks so fun, in my opinion. The mathematical part of the algorithm was all implemented correctly, but this library still ended up being vulnerable to a bug that completely nullified the security value of the math. This is one reason why people say you shouldn't build your own cryptography libraries, at least not unless you really decide to try hard to know what you're doing. The fact that the algorithms were implemented correctly, yet we could perceive some important facts about the system, makes this an example of a side channel. Timing attacks are a subset of SideChannel attacks, where the attack vector is based on how long the system takes to do something. There are a ton of examples of fun SideChannel attacks, but let's talk about one that's relevant to Python web developers. This attack caused websites that enabled gzip compression to reveal secret information to an attacker. So, in 2013, Django announced that you should disable gzip compression on all your websites because it can lead to defeating Django's cross-site request forgery protection, even if you use HTTPS. Gzip compression itself is pretty cool. It makes web pages shorter, which means that they are faster to send over the wire. But apparently, gzip compression allows a third party to guess a user's secret CSRF token. The problem was that you could determine secrets from web pages based on the length of the web page, if the person serving the web page hadn't been super careful. I'll explain the basics of cross-site request forgery, and then show you how gzip and HTTPS work together. After that, you'll see how the attack works. Cross-site request forgery protection is the idea that Django will give you a token that allows you to use a web form, like a login form, and have the server know that it's really you using it. Fully understanding cross-site request forgery isn't required for this section. What you need to keep in mind is that the server is sending a secret token, and an attacker wants to reveal that secret. To demonstrate the attack, I'll bring back the earlier login form since it looks so nice. Django gives you a little secret token to verify it's you doing the post request to the server to log in. I'll add that as a hidden input here. So there's a random value here. The server had to send it to you, and it really wants to make sure no one else knows it. If someone else knows it, then the security protection goes away. One of the best ways to protect information as it goes across the internet is to use HTTPS, hence the little green lock icon. HTTPS does a good job of making sure no one on the internet can read the contents of that CSRF token, because no one can read any of the communication between the server and the client. One thing HTTPS does not protect, however, is the actual length of the HTML content. That's fine here, since all CSRF tokens in Django are the same length. But let's turn our eye towards gzip. Gzip's whole purpose is to make HTTP responses smaller. That way, pages load faster. The way this compression works, more or less, is you take parts of the text that are similar, and you save space by saying them only once. I'm simplifying, but there you go. There's a lot of repetition in HTML pages. All those close tags end up. Here, the compression is identifying repeated text, so it can make the compressed document smaller. That's all you need to understand about gzip and CSRF to understand the attack, so let me show you how the attack works step by step. Here, I've put in a placeholder for 9 characters of arbitrary text in the HTML document. If the text is similar enough to the CSRF token, the document will compress shorter than if the text is totally unique. I'll pause here for a sec to make sure that's all sunk in. If the attacker can get arbitrary text into a page using gzip, then they can figure out the CSRF token. The hard part is actually exploiting this. How do you end up with the ability to put arbitrary text in someone else's website? Well, okay, I guess websites will pretty often copy query string data into the page. From here, the rest is history. In 2013, some researchers figured out a way to build a working exploit that lets them mount an attack. They called it Breach because they like clever acronyms, and they said it works in under 30 seconds with 95% accuracy for guessing a CSRF token of 32 hexadecimal characters. The reason is because they can do it guessing 1 character at a time. A useful side-channel attack often has the property of letting you guess a complicated secret 1 component at a time. I'll bring back that graph from earlier to let it sink in. This is a graph of how many guesses you need to guess the secret if you can guess 1 letter at a time, compared to having to try each possible complete value. This timing attack affected Python web apps in 2013, but this attack was one of a number of side-channel attacks that were ripping through web apps in the early 2000s. One of these involves an internal piece of the Python programming language called Python Hashseed. This attack is not a timing attack per se, it's more an attack on timing, and that's the kind of joke that cryptographers find funny, so I hope you'll permit the tangent. The idea is, if you know how Python's hash tables work, you can take a regular web application circa 2005 and slow it down to a crawl. This is because certain web applications were reliant on the hash table data type. Sadly, this picture is not the kind of hash that I mean. I'm talking about the computer science term, which is what Python uses in its dict implementation. Anecdotally, hash functions and hash tables are named that way because you take something, chop it up, and move it around, just like, for example, a delicious corned beef hash. Do you have corned beef hash in Australia? Does this joke work at all? Well, moving right along. Anyway, if you have a website that lets you search for things, you might have a URL that looks like this. If this site is written in Django, that will get parsed into a dictionary that looks like this. Dictionary is how Python spells hashtable, which is a standard data structure in programming. Adding or accessing 1 key in a dict is supposed to be fast. In fact, that's the whole point of using a dict for this stuff, is that you can look up things fast, whereas a list you'd have to iterate through the whole set. Hash tables aren't made of magic, though, they're made of math. The point of the math is to put each dict key in a different place in memory based on a hash function. If you're ever unlucky enough to have 2 keys that want to be stored in the same place, then performance will degrade until it's about as slow as a list. In 2003, Dan Wallach and Scott Crosby showed that if you insert 90,000 items into a Perl hash table, it takes 2 seconds normally, but 6,506 seconds if you can make all those items collide to the same hash value. We can use the same attack against something like Django. Parsing the query string into the request.get object can be extremely slow if the query string is constructed in such a way that all the keys generate collisions. The solution the Python team went with, which is what Dan Wallach and Scott Crosby suggested, is that instead of hashing the data we're given, we hash the data plus a random value, which is generated at Python process start time. If we do that, the attacker doesn't know what we're really hashing, so they can't choose values that all collide. This random value is called the Python Hashseed. As an appendix here, excuse me, if you provide random data to the hash function, but you use a bad hash function, Dan Bernstein will sit in his office at UIC and do some math, then make a Python script that undoes all the security gains of the randomness. For a good time, read pep456 to see why Python switched to a new hash function in Python 3.4. The demonstration code on the SIP hash website is a really fun read. And now you have all the pieces you need to understand maybe the most famous timing attack definitely in the past year and maybe in the past 10 years. I'm talking, of course, about Meltdown Inspector. This is the logo for Meltdown made by Natasha Eibel. Meltdown is a timing attack against Intel CPUs that was announced in January of this year. Can I get a show of hands for how many people have heard of Meltdown? Cool. Keep your hands up if you think you understand Meltdown in depth. Aha, okay, great. If your hand is down, don't worry. My goal is to explain enough computer architecture in the next 5 minutes that you can read the paper and understand the issue in its full depth. Ready? Here we go. Here I'm showing a grid of memory slots starting at index 0 all the way up to 2 to the 64. Technically 2 to the 64 minus 1. It's 64 because I have a 64-bit operating system like I'm pretty sure everyone in this room. This is virtual memory. Virtual memory is accessed by number. Programs written in C and other languages can access memory locations by number. Another thing you need to know is that some of these ranges are reserved by the operating system kernel for its own data. I've marked those in red. Some areas are for the program. I've marked those in green. Programs are not supposed to be able to read memory from the kernel or, in certain cases, from other programs. A program can access data by treating memory like a giant Python list and indexing into it with a number. Here is a program that might read data from a memory location it has access to. You can see we index into memory with a number. Main memory takes about 100 nanoseconds to access, which is quite a long time for a computer. The CPU does 3 to 4 billion instructions per second, so 100 nanoseconds is actually quite a while. There's another thing you need to know, therefore, which is that the computer reorganizes memory so that data that was accessed recently is faster to access. Here I have a program that accesses the same memory twice. The first time the program accesses this location, the computer has to fetch the data from memory, and it takes the full 100 nanoseconds. The second time it's faster, probably 10 nanoseconds or less. Next, here's a program trying to access memory it isn't permitted to access. Memory 1 is marked red on the diagram. The CPU raises an exception if the program tries to access it. These data permissions can change over time, and the CPU sometimes has to wait for the latest permissions information to be available. With Meltdown, our goal is to guess what's in memory 1. Our strategy is to have the CPU leave us a hint by how fast memory 10 is to access. We're not going to be able to read memory 1 directly because the CPU will prevent it. But if we can get the CPU to leave us hints stored in timing, then we can get all the way to the value. I'll show you some C pseudocode that achieves this. By the way, this is going to be like the most dense slide in the presentation, so this is the moment to be like, okay, I've got this. Okay, so here's some code. It's going to crash, but it'll do something useful for us before it crashes. In this code sample, we access memory 1, which we're not supposed to. You can see that memory 1 is marked red. Depending on the value in that memory, we go print out some values from areas of memory we are allowed to access. Now the CPU is going to raise an exception because we're not allowed to read memory 1. But the CPU doesn't know that yet because the permissions are slow to access right now. Even though the permissions are slow to access, the data happens to be fast. So the CPU does what's called speculative execution. It goes ahead and computes. It determines that yes, data is an even number, so it does this load of memory 10. When the permissions finally arrive, the CPU raises an exception and undoes all the speculation. But there's one thing it did not undo. Memory 10 is now faster to access because the CPU happened to read from it, specifically because memory 1 was an even number. The system state has changed based on the contents of memory 1, even though we aren't supposed to be able to access it at all. Now we can use the same techniques we described earlier in this talk to gain information step by step about the full contents of memory 1. And now you know enough about computer architecture to go read the Meltdown paper if you want. So, goals for this talk were to explain timing attacks in Python software, and explain side-channel attacks in general to get you to a point where you can understand some of the more recent side-channel attacks that have been happening over the past year. I I really blew through this, so I'm out, and I will definitely take time for questions, anything you have here, and I'm also happy to answer questions afterwards. Thank you very much for being such an attentive audience, and that's where you can find me. I'm at Feldini everywhere, and especially at that Mastodon server. Thank you so much.
Thank you, Philip.
Aha! Ooh.
All righty. Do we have any questions? We have one here.
In the slide where you were measuring the time of string comparisons, you first encoded the string to bytes. Why did you do that?
Funny, I'll go back to that slide because it was a funny moment writing this talk. So originally, when I wrote this talk, you're talking about this slide, right? Does that look, yeah, okay, great. There's a way to write this slide, which is password equals password. Or even better, password is password. That will happen instantly because Python is referencing the same object in memory because it sees that these two strings are identical, so it just returns instantly and kind of breaks the example. So this is us encoding into UTF-8, which honestly you might do if you're taking input from a web application to make for a more reasonable timing example. That's why it's also encode UTF-8 consistently to kind of explain that the encode UTF-8 isn't it's happening on both sides, so it's not actually affecting the output, but it's providing different memory locations so that Python's triggers about like is thing equal to thing not kicking in for this example.
Any further questions? Yes.
Ooh, I think that one doesn't work and he's back there, but we'll find out.
Thank you so much for the talk, and I especially liked your last foray to helping us with Meltdown. And my question is about that. We've been experiencing side-channel attacks for quite a while. This seems like now, anyways, it seems very obvious that that would be a problem. How come it took so long for us to find it?
Boy, what a great question. That I don't have a strong answer to. One thing I will say is that at a panel of security experts, I think at Black Hat earlier this year at a different security conference, someone asked the question, do we think Spectre and Meltdown are one-off attacks, or do we think that this is going to be like when we discovered buffer overflows and it's going to be the next 10 years of side-channel attacks? And if you've been paying attention to security news recently, it does look like this is going to be the next 10 years is kind of undoing what happened with speculative execution, the same way that we had to discover buffer overflows and then fix them. I don't know why it took us this amount of time to realize that this was going to be a problem. You know, I happen to have known some people who had like some Cassandraic warnings 5 years ago about like, hey, isn't this a possibility? And then being like, no, this could never happen. Computers are hard.
As a side note, I do believe one of the earliest CPU-based timing side channels that I've heard about was Colin Percival's work on hyperthreading back when that first showed up, and that was significantly many years ago.
Yep.
Just to continue on from that a little bit, the first paper I've seen talking about side-channel attacks due to speculative execution was 20 years ago when Intel first started introducing speculative execution. So it hasn't taken us that long, it's just taken us that long to accept it. I was actually hoping that you could have given an example of a side-channel attack that was not timing related. I know this talk was timing related, but I was hoping if you had an example.
Python Hashseed is technically not a timing attack, but is a side-channel attack.
There is that, yes, true.
Additionally, I mean, there's a lot available if you go look around, and I'm happy to talk about more examples during the break or some of the time. I think we had some questions over this way.
Got one up front. Hi. Before this, I'd never heard of timing attacks personally. Great talk, loved it. Thanks so much.
Thanks.
Just curious about the double equals comparison. Do you know if Bandit picks that up, like the Bandit testing tool?
I don't know, and that's partially because I've never heard of Bandit before.
Yeah, yeah, it's fairly new. I haven't used it myself, but yeah, I'm looking for security things in code via AST and it's apparently quite popular.
And it's tricky because, like, you know, most of the time doing a double equals comparison probably is what you actually want.
Yeah, a good thing.
It's just that there are certain security contexts like password checking or basically anything where this is a secret value where you probably want a constant time compare.
Yeah, thanks.
Got some over that way as well. Fight, fight, fight.
Thanks for a great talk. I guess this is very useful to understand things like Meltdown, but what would you suggest that we take into our mind when we go back to our Python applications at work or in open source?
Great question. This talk started partially because I wanted to understand Spectre and Meltdown and have an understanding of like the principles that underlie that foundation. And so the big takeaways for me, as with like every talk that I give, is this stuff is knowable, and it's knowable not without having to have like a full CS degree, and it's knowable without having had to take a course on computer architecture. Like, these things are understandable. Additionally, just to really drive home, please, 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 please don't write your own cryptography software. Please, please, please don't write your own cryptography software. And so the takeaway is, here was me talking for 20 minutes about why you shouldn't write your own cryptography software. But another takeaway is that, you know, to his point about tools looking for potential security concerns, if you're working in your day job, you're working on an open source project, when you are sending secret values around, even if you are using a cryptography library that you trust the cryptography library, make sure the way you're using it, like, now you know about a way you can test it to see if you're accidentally leaking information. And the fancy term for these types of timing attacks is called an oracle, because you can basically keep asking it questions until you get the thing that you want to get out of it. And it's actually still, unfortunately, easy to implement or to add correct cryptography libraries to your system, but use them in such a way that you are unknowingly revealing an oracle to guess that secret information. And so, you know, another way of phrasing SideChannel attacks is that the attack isn't on the wall, or isn't at the core, it's on the borders, right? So anywhere you're implementing another system, pay attention to the borders where data is flowing from one border to the other, and make sure that you really understand all the properties of that edge case.
So there's fixes that came out for the Meltdown attack, for example. How do these fixes actually fix the issue? Do they prevent reading through the cache in speculative execution, or do they wipe caches, or what are they doing?
That is going to be more the domain of the paper, and if someone has the answer, we're going to save this session for questions, so we'll take comments after the session and we can share that knowledge. But one of the ways that it does it is to just greatly reduce the amount that it's doing speculative execution. Part of the panic when Spectre and Meltdown came out is that we just saw across the fix showed like across the board CPU capacity reductions in the fabric of AWS and Google Cloud and all these places. Like, suddenly CPU capacity just went down because now they're no longer doing speculative execution in some cases. And so there's work trying to kind of give us that back, but it's entirely possible that there isn't a great way to do this safely. And even like the most recent kind of Spectre Meltdown related attack was an attack against one of the things Intel did to prevent the earlier attack, right? Like, computers are hard. And it could just be that it turns out that this is not a viable technique for increasing CPU performance. We don't know that yet. We're still kind of figuring out the edges of this technique.
And that's all we have time for.
One thing I will say, just real quick, I like playing tabletop games, and I have a couple with me. If you want to play tabletop games, come see me. And tomorrow I am running a chocolate buff. So I have chocolate from my travels around the world. If you want to share in some chocolate and bring your own, follow the socializing channel or follow me on Twitter, Mastodon. I'll post about the chocolate buff tomorrow sometime.
Please thank Philip.